This is our video for AP Calculus AB, section 6.1, and section 6.1 is all about what we call slope fields. And if I remember right, we did some slope field work on the first day of school. We're going to come all the way back around and kind of finish up the year with this. So we're just going to do the first two examples here, numbers 1 and 2, and we'll save the other ones for class. Let's see how you did with this, and so let's go ahead and start with number 1. So the instructions say draw a slope field for each of the following differential equations. Each tick mark is 1 unit. So let's talk about the idea that we're dealing with differential equations here. If maybe you remember that a differential equation is any equation that has at least one derivative in it, and you can see, of course, this first one, dy dx, that's a derivative equals x plus 1, and so this is a differential equation. So to kind of think back on what this means, dy dx stands for the slope of the tangent line, and so what this is essentially saying is that the slope of the tangent line depends on the x-coordinate plus 1. So one of the ways you can handle this is you can make a little table. We'll start to see a pattern emerge from this, and then we can kind of depart from the table, but I think the table will be helpful for us to get started. So the input is going to be x, the output is not going to be y, the output is going to be dy dx. So in other words, for every x coordinate, you're going to have a particular slope at a point, or local linearity, I think was the term we used at the start of the year. So we're just going to go input, output, see what happens. So I'm going to plug in a 0 first. When I plug in a 0, dy dx equals 0 plus 1, so that's 1. Let's go ahead and graph that. That's saying that whenever x is 0, the slope is 1. So whenever x is 0, we're talking about the y-axis. And so all along the y-axis, I'm going to have a slope of 1. So it's going to look something like this. If you remember, we draw these little tick marks in, these little hash marks maybe, something like that. And we have a positive 1 slope at each of those spots. You might wonder how I got that angle. Like when I was looking at this slope field, I was trying to aim it at this point, which would be a slope of 1, of course. So I don't connect them, but I'm aiming at that, knowing that that would give me a slope of 1. Okay, let's try some more. Again, feel free, like always, at any time to stop the video, pause the video, and then try this on your own, see how it goes. So dy dx equals, if I plug in a 1 for x, you get 1 plus 1, which of course is 2. And so I'm going to come over here whenever x is 1. That's going to be this vertical column right here. So I'm going to have a slope of 2 at each of those. So I'm going to make it a little steeper, well, twice as steep technically. And again, I'm aiming at the point, that one's off by a little bit, I suppose. I'm aiming at the point that would give me a slope of 2. Those look pretty reasonable. Let's do one more moving to the right. I'm going to plug in a 2 for x, and of course dy dx is 3 when that happens. The steeper these get, the more difficult they are to draw. See what I can do with this. These are looking pretty good. And again, this is describing this entire vertical column. Let's go ahead and go to the left and see what happens there. If I plug in a negative 1 for x, dy dx equals negative 1 plus 1, which is 0. So in other words, whenever x is negative 1, the slope of our graph is 0. So 0 slope all along this vertical pattern where x equals negative 1. 0 slope, of course, is a horizontal line. So we get these nice little horizontal tick marks there to signify that. And then do 1 or 2 more here. So maybe negative 2 and negative 3 would be appropriate here. So negative 2, when x is negative 2, dy dx is negative 1. Whenever x is negative 3, dy dx would be negative 2, just by going input, output. So once again, we have these vertical patterns. So this is where I think we can start to draw a broader conclusion. We'll make that here in a second, but haven't we seen only vertical patterns here, right? All the slopes are going to be the same in that vertical column. I'm going to go one more over here with my negative 2 slopes. Starting to hopefully see a picture develop. Let's talk about the generalized pattern here. Here it is. It's really simple. Whenever dy dx depends only on an x value, you're going to get a vertical pattern. Whenever dy dx depends only on x. Now if there's a y in there, it's different. But if dy dx only depends on x, then we have a vertical pattern. So I'd encourage you to think about what this this general pattern is, if I were to think about what we call a solution curve, take a second, think what this looks like to you. And I would say, I hope we agree on this, this looks like a parabola. So if I had a particular, if I was looking for a particular solution curve, had an initial condition, maybe I could draw in, let's try that again. Could draw in something like that. That would be hopefully a pretty good solution curve. One note about this, if I do, well, let me be a little more official about this. Let's say I was told that the solution curve had the initial condition y of -1 equals 1. So in other words, when x is -1, y is 1. That would be this point right here. If I were to draw a solution curve in for that, it would look something like this, like so. Let me do a little bit better. There we go. That's about what I was looking for. A couple of notes about that solution curve. Number one, has to be a function. And this one is obviously a function. You can see would pass the vertical line test. Also, it needs to actually pass through that initial condition point. It needs to go through the point -1, 1, and it should not go through any other points that we have marked here. It's not that it doesn't go through those, we just don't know that it does, so it's safer to avoid those altogether. So that would be what we call a solution curve. Okay, let's go ahead and do another one. Let's do number 2. There we go. So with number 2, we've got a really similar looking start here. We've got dy dx equals 2y. So notice a couple of differences though. First of all, dy dx is not in terms of just x, it's in terms of y. So we're going to see a different pattern here. And of course the 2 is in there as well. But overall it's still just a differential equation. And so we're describing the slope of this particular graph in terms of, in this case, 2y. So for me to create a table, my input's going to have to be y, and my output's going to have to be dy dx. And so like before, let's go ahead and get started. So when y is 0, dy dx is 0. So when y is 0, we're describing the x-axis. So all along the x-axis we would have horizontal little slope field marks. All right, so maybe when when y is 1, dy dx would be 2 times 1, which is 2. So let's see here. That's going to be getting pretty steep pretty quick. So these little tick marks will look something like this. And then finally when y is 2. When y is 2, dy dx is 4. These are very steep, of course. Almost going to look vertical. And we're looking at something like that. Let's cover the lower half of the graph too. So when y is -1, y is -2. So when y is -1, the slope dy dx is -2, and then of course when y is -2, our dy dx is -4. So a slope of -2. Let's do a little better than that. -2, -2. All these slopes here. You're starting to see the pattern emerge, right? Instead of a vertical pattern, these are all going to be horizontal patterns. And then a -4 slope looks something like this. That last one's maybe a little bit much. There we go, something like that. Okay, so there's our slope field. We can compare it to number 1 there. You can see that with number 1 we had that vertical pattern because dy dx depended only on x. Number 2 though, we got this horizontal pattern because dy dx only depended on y. Now like I said before, if dy dx depends on both x and y, it's neither vertical nor horizontal. It's actually going to be sort of an angled pattern. As you can see, this pretty clear pattern emerge with numbers 1 and number 2. So as far as a solution curve goes, this one is maybe a little bit less clear than the one we just did with the parabola. This one actually ends up being an exponential growth. We're going to be looking at that in section 6.2. Exponential growth or decay. So let's say that we had the initial condition of y of 1 equals 1, something along those lines. Of course, that's that point right there. That means our solution curve would have to go through that point. It would look something like this. It's an exponential. Maybe you can see that emerging from the pattern of slopes there. Got a horizontal asymptote there on the x-axis, and then as we go from left to right, it's going to start going uphill. If we had a solution curve whose initial condition was down here, that'd be a similar pattern. It would just be decreasing instead of increasing. I chose that one right there. Let's say I'll just draw that one in there too. So let's say we had a different initial condition, like y of 1 equals -1. So that would be this point right here. That solution curve would look very similar. It would just be down below and decreasing instead of increasing. So either one of those could be the solution curve, but not both. We'd have just one initial condition, and one initial condition would be describing one or the other. So that's it. When you come to class, we will be working on doing more of these slope fields and maybe a few solution curves as well, and I will see you then.